student chapter seminars.
Yeah.
Hi, Xiaoheng. Nice to meet you.
Nice to meet you. Thanks for inviting me. Yeah.
Yeah, it's our great pleasure.
Yeah.
And before your presentations, we would like to have a small talks with you to get some experience or to see if we can learn something from you. As
Sure.
I know, yeah. As I know, you have recently graduated from the University of Pennsylvania. I was very curious what motivated you to start your research in the architecture materials?
Yeah, that's a pretty good question. So basically, when you get into the PhD program, you generally you should follow the research path of your advisor. So before I joined the Penn, I didn't learn so much on architecture materials. However, because our lab's name is on the architecture material lab, so we have got very good research history on the architecture materials. So that's the opportunity for me to learn more and to understand more on architecture materials.
Yeah, that sounds cool. And what do you think is the biggest challenge when you look back for your entire PhD life?
Yeah, the biggest challenge is that I think that is a transition from a dependent researcher to an independent researcher. So basically, in the first 2 or 3 years, generally you should follow your advisor's research ideas, and then you should follow his path. And however, if we'd like to graduate, then it's in the last 2 or 3 years. Generally speaking, you should learn more. You should know more than your professor knows. So that's the reason you should transit from dependent to an independent. You should have got your own idea. You should know what the tools you may need to solve the questions you face. So this is a very hard transition for most of the PhDs, in my opinion.
Do you develop your independent research from your previous works that is given by your advisors, or you just come up with some new ideas?
Yes, generally speaking, the first 2 or 3 years, basically, you should follow the path of your advisor. Then finally, with more and more deep understanding, you should know more than what your advisor knows. So in the last 2 or 3 years, generally speaking, you should follow with your previous projects, you know what's the possible future directions. Then in the final 2 or 3 years, you should try to solve some questions you raised in the first 2 or 3 years on your own. So this is the challenge. Yeah.
Yeah, that's a great suggestions. And how do you like your life at UPenn? And how do you think about your current group?
Yeah, it's Penn is a pretty good firstly, Penn has got a very good reputation, and with this type of reputation, so the most of our research are quite novel. So we try to pursue high impact and high quality research outputs. So the life at Penn is very challenging, and most of the and also your colleagues, the other PhD students are very talented. So basically speaking, also the advisor is very nice. So even if you have, because we are an experimental group, so if we have got some numerical or any theoretical questions, we can find appropriate, very qualified advisor to give us some advice. So basically, Penn is a very challenging challenging environment here, and also a very productive environment.
Is there many collaborations with other group in your department?
Yes, I've got the collaboration with another new PI here, Professor Altman Tachiliano, with one of my PhD thesis, one of the parts of my PhD thesis, and also we have some collaborations in our lab. We have great collaborations with other theoretical guys, and also with Dr. Maybe you know Dr. Prashant Purohit. One of my colleagues is actively collaborating with him right now. And basically, it's a very small group, but very productive, and everyone is glad to do the collaboration work and very friendly, open with that.
Yeah, that sounds like a nice place for the researchers. Is there still any opening in your groups?
Yeah, that's a tricky question. So at this moment, I think we have some openings. We have fundings, and but you know that it's a very challenging challenging situation at this moment. But I think that we have some openings right now.
Oh, that's great. And just final questions. Do you have any advice for the current or the potential graduate students?
Oh, that's a big question. So,
Yeah.
I can only share my personal experiences that I think that you should not for PhD students for the first 2 or 3 years, you should not try to tackle a nature or science level question. So basically, you should start with a simple questions you can handle, and starting from that, maybe you have got small publications, and after you have got know the pattern and you know how to find the problems, you have enough experience and tools, then you can try to target on more advanced or more novel research questions.
Yes, just like climbing a mountain,
Yeah,
start from the bottom.
yeah, you should start from the bottom, and yeah,
Yeah, thank you so much. Now you can share your screen.
yeah.
And let me have a short introduce for the Dr. Xiaoheng. Dr. Xiaoheng Zhu is a recently graduated PhD student from the Department of Mechanical Engineering and Applied Mechanics at the University of Pennsylvania. His research interests majorly focus on designing architect materials and structures with enhanced Fulian characteristics, such like fracture toughness, buckling resistance, and impact resistance. And his past research projects include bamboo-inspired architect structures with enhanced damage tolerance, and bio-inspired distributed non-deterministic lattice design algorithms, and pneumatic controlled architect materials with tunable buckling assistance. And congrats to Xiaoheng Zhu. His recent research works has been published in the Science Advanced journals. And now it's your screen. I will mute myself.
Yeah, thanks Yanran for your introduction, and a brief introduction. My name is Xiaoheng, and right now I just graduated from Penn, and today's talk, the topic I'm going to talk today is called the design of non-deterministic architecture structures via bio-inspired agents. So many of people here may heard of the architecture materials. So the first question I'd like to introduce here is what is architecture materials? So architecture materials developing, here I give a history map of the architecture materials. Basically speaking, in 1940s, generally speaking, for engineers want to improve the materials, mechanical property, especially the failure property, they need to focus on the microstructure modification. So which means there are some tools like the grain refinement, the phase transformation, so that they can try to toughening the material. Then with the development of the manufacturing method in the 1970s, there are researchers introduced the idea, engineers introduced the idea of the try to modify the materials in the micro scale. In this background, the composite design emerges. So the composite design, here I show some examples like the carbon fiber reinforced polymer, the metal composites, or recently there are some called the nature-inspired composites. So between the micro scale and the macro scale, there is in 2010, because of the development of the 3D printing, there is a new level of the materials. This is called mesoscale materials. So for the mesoscale, the architecture materials emerges in this field. So for example, I show some, you can see that these literatures are relatively new. So you can see that engineers try to use some topology or try to use some voids and try to deflect the crack. In that case, try to improve the failure property of materials. So this is called architect materials. So with the recent developments of the 3D printing, right now it's a lot of researchers try to control the internal geometries of architect materials via 3D printing. So here I only give an example of the 3D printing technique our lab have. In our lab we can do the FDM. This is called the fused deposition modeling. So basically speaking, these type of machines, that the nozzle can be heated, in that case to fuse the materials and do the extrusion to form the shape. So here I can, this example is the bullet gun structure. So you can see that for each of the layers, yes, have got it's a very specific angle, in that case to deflect the crack propagation. So another example, another technique we have in our lab is called the DIW, so direct ink writing. So it's very similar like the FDM. For the DIW, the nozzle is not heated. Instead, the material itself is kind of like between the liquid and the solid. So we use the pneumatic pressure to extrude the materials out and to form out the shape. And the final technique we have here is called the DLP, digital light processing. Basically speaking, we use the photopolymer and use the UV light to cure the materials to form the shape. So with all of these advanced manufacturing methods, right now engineers have got the opportunity to do some so-called bio-inspired art composites. So for the bio-inspired composites, there are several examples, like the bio-inspired composites with high impact resistance. This one is from Basler's group. This is the nature-inspired architect materials with enhanced impact resistance. Another example is the contour-inspired composite. It's very similar. So it's using the heterogeneity, try to deflect the crack propagation, in that case to deflect the crack and improve the damage tolerance. And finally, is our group's work. This is called the auto-inspired composites. Basically speaking, we use the heterogeneous printing. This one is the DIW printing. So to achieve high toughness soft materials. So with all of these bio-inspired composites, we can see that basically speaking, what they are doing is that they try to extract the characteristics from materials in nature, and then they mimic these characteristics into their materials or into their structures, in that case to achieve higher damage tolerance or in that case. However, for materials in nature and the materials in engineering or in engineering, it's quite different. So that's the reason we say that we try to do some comparison. So for the structures in nature, just like what we showed in the previous slides, they are quite deterministic. So which means after the engineers confirm the design scope, confirm the design parameters, they will fabricate thousands or even millions of the same samples. In that case, these samples may have got low defects tolerance. What I'm saying here is that, for example, you can assume that for the 3D printing or the CNC machine, after you finish your one part, if there are single defects, the entire part should be abandoned. It cannot be used. However, for the structures in nature, it's quite a different story. For the structures in nature, they are not strictly deterministic. For example, here I show an example of the honeycomb. We know that before these bees to construct the honeycomb, they normally don't have a construction map, so they didn't have the design. What they are doing is that each of the agents, each of the bees will make the construction decision on its own. So which means that agents can only have just local information and make the construction decisions based on the local environment. For example, if you cut the honeycomb and to see what's inside the honeycomb, you can see that here it's an area honeycomb. The bees didn't deposit any materials inside. This may caused by the obstacles or caused by the physical constraints, etc. So for this type of the structures in nature, we can say that they have those relatively higher tolerance to defects. So even you can assume that in a honeycomb, even there are some missing beams, it's still okay. The agents can still work over there and try to construct new structures in that area. So they are adaptive to the environment. So with the development of the robots, so we can in the recent past 2 or 3 years, we did see that this type of the distributed manufacturing method has been emerged and been studied by the robotic hardware guys. So here I show an example of the drones, flying drones. This one published in Nature. So what they are doing is that they didn't give specific requirements for these drones. Instead, the users just let these drones to fly over the construction space and make the construction decisions based on the local environment, based on the local structures. So another example is from our department, Professor Minsky's group. This is a microscale robots. So for these microscale robots, these robots can do some reaction, have some reaction with the local environment. In that case, they can align together and they can do some specific actions, such like jumping. So that's the reason we say that with the development of the distributed agents, agent-based non-deterministic artificial structures design is now possible. So to start with, there are some key questions we need to ask. The first one is called, what rules should agents to follow and to generate useful structures? Because basically speaking, like the bees or like the ants in the nature, it's a relatively new idea, and we at the beginning stage of this project, we try different motions, we try different rules, such like the Brownian motion. In this case, we just let the agents to deposit materials randomly in the design space. You can see that it's like the form-like structures. And also, we try to mimic the growth of the Voronoi structure. So you can see that Voronoi structure is commonly seen in nature, like this is the dragonfly. You can see on their wings, there are some Voronoi structure. So we mimic that. You can see here is have got the primary structure implemented with secondary structure in that case. And the final the final and most important rules we show in this work is called the bifurcation growth. So for the bifurcation growth, we mimic the growth of the neural network. In that case, the single beam can be bifurcated into two and to form like the structures. So at the beginning stage of the project, we try to code and try to design new rules. Then we cannot, because it's a new idea, we cannot design the rules on our own. We should consider the hardware capability right now for these robots can follow. So we need to consider whether these materials should be additive or subtractive, and how the agents can move. This is called the local motion in robotics. And also we should consider the sensor modality. So for the scope of this work, because it's relatively a new idea, we have got 3 important parts. The first one is that we should have some rules for distributed agent. We majorly focus on the bifurcation rule. So with all of these rules, then we will use these rules to generate thousands of the architecture structures. So with all of these structures, this is called the rule structure relations. So after we get the rule structure relations, the next question for us is that we need to extract the mechanical property of these architecture structures. For here, we use 2 parts. The first part is because we have thousands of structures, we cannot fabricate using the 3D printing to fabricate these non-deterministic design endlessly. So what we are doing is that we calibrate our finite elements model. So here we are using the UMAT in Abacus. So you can see that with our calibration, the crack propagation is very similar between the apertures and our experiments. So in that case, with the calibrated finite elements model, we can extract the energy dissipation and also extract the strength, the maximum loading by the through the finite elements. And finally, for this relation, this is called a structural property relation. So for the core of this work is called the rule structural property relations. So finally, we apply our rules into a heterogeneous design space and try to have some applications. So let's start with our rules. This is called the bifurcation rule or the exfiltration rule. So it's a real new idea. So basically, we have got a design space, and inside this design space, we let the agents to deposit materials freely. So for example, you can see that what if a single agent inside of these structures, it will follow the existing structures, and once it reaches the node, it will turn the angle and do the bifurcation and deposit new structures. So the length of the structures and also the length of the beams and also the bifurcation angle is controlled by a non-deterministic normal distribution implemented into the structures. Implemented into the agents. So you can see that basically speaking, we use two functions to control the stochasticity level of our artificial structures. The first one is the probability of the deposition length, and the second one is called the probability in the bifurcation angles. So we use these two parameters to control the stochasticity level. So with all of these setup of the rules, we try to study the rule structural relations. As I mentioned, that there are two sources of stochasticity in the beams and stochasticity on the bifurcation angle. So here we show the case that by easily tune the two parameters, we can generate from highly regular lattices to a highly stochastic lattices over here. So after finishing these things, we do the finite elements validation. So we are using the UMAT. So from this experiment, you can see that for the UMAT, we just once the element reaches the yield strength, the elements will be deleted automatically. So you can see that the crack propagation path is very similar between the finite elements and the experiments. So you can see that from the loading curve, the energy dissipation and the maximum loading, they are in the same level. And by the way, because we treated these structures, treated these things as structures, so for here, we're using the energy dissipation instead of the toughness to characterize the failure characteristics of our architected structures. So with all of these rules and setup, the next question for us is that we try to further refine our rules. So that's the reason we go over into the nature and try to adding some local interactive functions into agents. So we take the ants as an example as the left side. You can see that for the ants, they have some the first function we add is the environmental coordination. So for the ants, you can see, oh, I'm sorry. So for the ants, you can see that in the nature, if a single ant find out some food or some leaves, what they are doing is that they will ask their colleagues, the other ants to go to that space and to move the obstacles or to move the food together. So in this work, one of the Harvard group, they are doing is that they use the agent to mimic the behavior of ants. So you can see that these ants will try to gather in the high light intensity area, and inspired from this type of the hardware capability, the first function we add into our agents is that we let these agents to have some sort of the environmental coordination. So for example, we can let our agents to deposit more materials in hot weather and to deposit less materials in cold weather. In that case, by implementing a heat map, then we can have got some heterogeneous material, heterogeneous structure. So you can see that this is AML, our lab's name. We have got more materials in the high temperature area. So the second function we add is called the boundary defect detection. So we also, this is the same group in Harvard. It's also the example of ants. For example, if you trap the ants, if a single ant find out a way to escape the trap, the ants will send the signals to the other ants to let the other ants to follow the path and to escape the trap together. So in this case, they mimic this behavior in robots. So you can see that a single ant find out a way to escape, the other ants will follow the path to escape as well. So that's the reason we add two functions. The first function is called the boundary detection. So for example, if a single agent detects there is another node nearby, it will slightly change the deposition, slightly change the angle and to merge to that node to increase the nodal connectivity. So another example is if the single agent detects another beams nearby, it will not do the bifurcation. Instead, it will deposit materials directly through there to improve the material efficiency. So another function we add is called the local communication between agents. So for example, if two agents to detect each other nearby, they will send signals together and to do the merge. So they will merge together and to form a single node instead. So with all of these local functions, we did see that this is a property map. The left hand side here is the tensile strength. You can see that with the local interactions, we can reduce the relative density, and at the same time, we can maintain the same level of the tensile strength. And also for the energy dissipation part, you can see that with the local interactions implemented into agents, you can see that the relative density decreased. However, the energy dissipation still maintain the same level, and for some cases, it's even improved. So with all of these things, with all of these tools functions has been characterized, the next question for us is what's the possible application? So we know that in engineering, and both in engineering and in nature, we know that most of the design space are not homogeneous. There may some physical constraints, or there may some obstacles inside. So that's the reason inside of a homogeneous design space, we randomly cut voids. So you can see that we cut two holes. And then we know that because of these holes, there are some stress concentration areas inside at the ellipse of these holes. So that's the reason what we are doing is that we put that the stress map into as a heat map, and put that into our platform, into our rules, and then we let the material let the agents to deposit more materials in the high stress area. And you can see that for our structure, these two structures have got two same relative density. However, you can see that for our structures, we can achieve higher loading strength, and at the same time, we can have higher fracture strain, and in that case, which contributes to the higher energy dissipation. So you can see that in our property map, our rules, you can see that can maintain the same level of the tensile strength, while can increase 15% on the energy dissipation. And remember, because it's a single material, so even 15 or 20% on the energy dissipation, or some people call this toughness, is a very huge improvement. So summary, what we are doing in this work is that we design simple rules for distributed agents that only have access to local information. And then we implement a rule structure property relations to generate high fidelity finite element analysis and 3D printing prototypes from the generative structures. And then we add some local interactive behaviors into these agents to further improve the structural performance. Then finally, we are doing some non-deterministic lattices. And finally, we found that non-deterministic lattices generated by distributed agents in discontinuous design space can have about 20% improvements on the average energy dissipation compared with regular lattices. And in the future work and in the ongoing work, we will collaborate with hardware researchers to realize these distributed manufacturing methods. So finally, we'd like to thank the funding agency from the NSF, the Future Manufacturing Grants, and also thanks my advisor, Professor Rainey, and our collaborators, Dr. Liu, Dr. Gosrich, and Professor Ying at Penn. So that's it. And any questions are welcome. Hi, Yanran.
Oh, hi. Thanks for your great works. And it's a nice presentation. Everything is very clear to me. And I have a few questions. The first one is you show me algorithms that you can design for the lattice structures with some stochastic properties. So do you when you compare it with the deterministic lattice, is the volume fraction of the material keep the same?
Yes, they are the same. So here is the property map. So for our final ones, you can see that the x-axis here is the relative density. So we can compare our structures with the regular lattices with the same relative density. You can see that our mechanical properties still improve.
Okay, great. And another question, so you mentioned that you used the UMAT in the FEM to simulate the fractures of the lattice. So what is the fracture criterion you use in your UMAT?
Oh, this is the Vomesis stress.
Okay, I see. Great. And a general question is that I really like your idea with this non-deterministic designs. So is it possible to combine it with the optimizations? Because I think the current optimization for the lattice may have many local minimums. So if you add some non-deterministic terms to it, maybe it can provide you a better result that close to the global minimums.
Yes, that's a good question. So what you are talking here is that it's on the structural optimization side. So basically,
Yes.
you can use some optimization tools, try to optimize the specific structures. However, the questions we propose here is that if we like to do some optimization, we prefer to do the optimization on the rules. So that's the reasons, for example, for agents, we can let these agents to be more clever. So for example, let the agents to have some more local functions in that case to improve the structures overall structures efficiencies. So that's quite so for the optimization for the robotics of the agents is quite different with the optimization with the topological optimization or any other method in the structural design from the structural design perspective.
Okay, thank you. That's all my questions.
Yeah.
Hi, Xiaoheng.
Hello.
It's a very nice talk and yeah, great work. I have one quick question. So actually, I think your work is like try to linking the property with the structure, optimized structure. Well, I'm just wondering, how is the compatibility with your design in computational with the design from you 3D printing? Like from your numerical, there is some responses different between the numerical validation with the experiment. It is based on the material property, or it is based on the a little bit different between your ideal design with what you really printed. So
Okay.
how the design and you really manufacture, how different they are, and is it very like very similar or very compatible?
Okay, I understand the question. So basically speaking, for the materials we are using in this work, so for the 3D printing materials, it's brittle materials. So from our simulation, we did see that the simulation and the final elements are have got very comparable. So however, if we fabricate these materials with more detailed one, then we did from our simulation tools, especially using the UMAX, we may not achieve very good alignment between the simulation and the experiments. So frankly speaking, for right now, the simulation tools we have in this work only limits on the brittle materials, not on materials with data materials. However, with the 3D printing technique, we also have some developments on the 3D printing technique in this work and try to reduce the deviation. So from our current manufacturing method, we can say that for the brittle materials, we can our experiments agree pretty well with the simulation.
Thank you, thank you.
Does anyone has any more questions? Well, thanks again for the Dr. Xiaoheng Zhu for giving us the online seminar talk today. It is very inspiring.
Yes, thanks for inviting me. Yeah.
Yes, you are always welcome, and all the best for your future careers.
Yeah, thank you so much.